Imagine you're overseeing operations at a mid-sized U.S. bank. Your Treasury division moves, let's say, $3.2 trillion in daily payment volume. It's massive. And you've deployed this state-of-the-art AI assistant to handle exceptions. You know, those incredibly pesky errors that hold up wire transfers. For a while, it seems to be working beautifully. That is, until Tuesday evening when a massive international wire completely fails and the money just vanishes into the ether. Welcome to this explainer, where we're going to dissect exactly how an artificial intelligence design flaw cost a bank millions of dollars, and more importantly, how we can actually build a bulletproof architecture to make sure something like this never happens to you.
Okay, let's dive right into this. I want to put you directly in the shoes of a forward-deployed engineer at Sterling Treasury Services. You're sitting there, staring at your screen, and you're looking at a $4.1 million failed wire to a Tokyo correspondent bank. The wire was submitted, the AI system processed it, but Tokyo never acknowledged it. Why? Well, because the AI assistant attempted to repair a missing intermediary bank code, but it hallucinated. It completely dropped the ball and inserted an 8-character string where exactly 11 characters were required for that specific routing corridor.
But honestly, the real nightmare here isn't just that the AI made a mistake. Look, AI makes mistakes, we know that. The true catastrophe is that this $4.1 million error wasn't flagged when it actually happened. It was caught during the end-of-day reconciliation. It was flagged a full 18 minutes after the Fedwire third cutoff. And what does that mean? It means by the time human eyes actually saw the error, the window to cleanly recall the wire had completely, permanently closed. It was exactly 18 minutes too late.
Let's actually walk through the exact timeline of how this unfolded on that Tuesday. So at 14:11, the wire is submitted. 4 minutes later, the large language model, the LMM, proposes a repair for that missing code. And here is the fatal flaw, right here. The LLM confidently checked its own work. It scored its totally malformed 8-character repair at a 0.94 confidence level. It bypassed a simple deterministic rule check and basically just said, yep, looks good to me. At 14:16, Fedwire accepts the message, and it just sits there, completely broken, until 17:42 when end-of-day recon finally raises the alarm.
So let's get into Section 1, the architectural flaw, using probabilistic systems for deterministic work.
To really wrap our heads around the root of this problem, we have to look at the massive paradigm shift happening in tech right now. Andrej Karpathy famously described this evolution as moving from software 2.0 to software 3.0, where LLMs essentially act as an entirely new programming interface. The context window is the program. But here's the reality check, and it's a big one. You absolutely cannot let these new probabilistic systems operate alone when the stakes are deterministic. Think about it like this. You have the Probabilistic Proposer, your LLM. It is brilliant at being creative, handling ambiguity, fuzzy matching novel problems. It's great at that. But then you have the Deterministic Validator. Think of rules engines like Drools or durable state machines like Temporal. These systems are rigid. They are reproducible. They are exact. The exact second you ask a creative probabilistic system to do rigid deterministic validation, you are inviting total catastrophe.
So the crucial point we need to take away is captured perfectly in this mantra: probabilistic on the outside, deterministic on the inside. This right here is the golden rule of agentic design in production. You can absolutely use an LLM to figure out what went wrong with a wire. You can even ask it to propose a fix, but you can never, ever let an LLM validate its own work, and you can never let it directly trigger a side effect, like actually sending a wire, without strict supervision.
And that brings us to what we call the 3-band boundary, which brilliantly illustrates how a secure system actually functions in the real world. Band 1 is the probabilistic proposer. That's where the LLM proposes a typed action, like a specific repair for our wire. Band 2 is the deterministic validator. This is a rigid engine that rigorously checks that proposal against stone-cold rules. And finally, Band 3 is the side effect layer. This is the dumb execution layer. The actual Fedwire submission only ever happens if, and literally only if, the validator gives a rock-solid green light. Let's actually crack open that middle band for a second, the deterministic validator, because it's built on 3 totally non-negotiable gates. Gate 1 is regulatory. This is where you're checking things like the U.S. Treasury's OFAC sanctions list and Fedwire formatting rules. No exceptions. Gate 2 is the system of record right contract. Essentially, does the LLM's proposal actually match the database schema? And Gate 3 covers your business invariants. These are your standard limit checks and dual control thresholds. If a proposal fails any of these 3 gates, it is rejected immediately. Boom, it never reaches the real world.
All right, moving on to Section 2, fixing the automation workflow, the Sterling application.
Now that we have this incredibly powerful three-band boundary framework in our tool belt, let's use it to diagnose Sterling Bank's internal workflow. Now, what's really interesting here in step 2 is that they currently use a rigid deterministic rules engine to try and propose repairs. And honestly, this is completely backwards because rules engines can only fix exceptions they explicitly have rules for, right? Which means 89% of their exceptions are just routing straight to human queues. This kind of generative problem-solving work is precisely where the probabilistic intelligence of an LLM should be utilized. It's the perfect job for it. But here, in step 3, we expose the exact fatal misplacement that caused the multi-million-dollar disaster from the beginning of our explainer. Sterling was actually using a probabilistic LLM to validate the proposed repair against the Fedwire schema and OFAC lists. This is the ultimate silent confidence trap. An LLM simply cannot reliably check regulatory invariants. Sure, it'll fail rarely, but when it does, it will fail confidently and invisibly. This validation step absolutely must exclusively be a deterministic rules or regex engine, no exceptions. Let's also just briefly look at step 5, notifying the customer. Sterling was letting the LLM generate the entire email. The diagnosis here is that it actually requires a hybrid approach. An LLM is fantastic for drafting a polite, really clear email body explaining the delay to the customer, but it needs a deterministic envelope around it. Why? Because legally required Regulation E boilerplate text must be in that email. If the LLM occasionally hallucinates and drops that legal text, which it will, you are instantly failing compliance. Which brings us to section 3, the golden rule and common pitfalls. As we wrap up this analysis, we really have to look at the dangerous traps that engineering teams fall into when they're trying to build controls. I want to ask you this directly, because it is a massive misconception in AI development right now. If your first LLM proposes a high-stakes banking action, is having a second LLM double-check the first one's work a valid regulatory control? It turns out the answer to that is a massive, resounding no. 2 probabilistic systems do not equal a deterministic guarantee. Think about it. LLMs are trained on similar, massive datasets. They share the exact same blind spots. If the first LLM makes a confident mistake, the second LLM is highly likely to confidently agree right along with it. Regulators will never, ever accept an uninspectable audit trail where your only defense is, well, the other AI said it was fine.
So, summarizing the 3 core engineering pitfalls you absolutely must avoid. Number 1, thinking 2 LLMs is a control. It's totally uninspectable. Number 2, validating at the end. Remember our disaster scenario? Catching errors in end-of-day reconciliation means you are catching them 18 minutes too late. Validation must happen before the side effect. And number 3, reverting to rules everywhere out of sheer fear. If you ditch the LLM entirely and try to use rules engines for generation, you completely kill your automation ceiling and you'll stay stuck at that 11%. And this leads me to a really critical question I want to leave you with today. I want you to look closely at your own agentic workflows. Where in your system is an AI checking its own work? Finding and fixing that silent confidence trap today is literally the only way to ensure you aren't the one dealing with a multi-million-dollar disaster tomorrow. Thanks for diving into this explainer with me. Take this framework, apply the 3-band boundary, and go build something bulletproof.